This graph charts a critical trend. The AI industry has hit a hard physical limit. We are maxing out our energy and compute capacity, crossing a strict efficiency bottleneck. Modern enterprise software relies on multi-agent systems, clusters of AI agents running continuous, autonomous background loops 24/7 to process data and execute code. The sheer volume of these autonomous loops is driving terawatts of unnecessary energy consumption worldwide. This week, researchers from MIT and Microsoft released a paper introducing a framework called Murakkab to solve this exact hardware crisis. Murakkab operates as a dynamic compilation layer that sits between your code and the hardware, and empirical tests prove it slashes AI energy consumption by 73%. For computer science students targeting 2026 placements, this is the new reality. The market no longer values basic app front ends. Engineering value is now measured by your ability to solve physical energy bottlenecks. The root cause of this massive compute waste is a structural flaw MIT researchers call the configuration conundrum. This diagram outlines a traditional sequential workflow. When you build a multi-agent system using these methods, you are forced into hard-coding every technical choice up front. The problem is that human developers simply cannot accurately predict how a dynamic, multi-step agent will consume tokens in real time. Because of this unpredictability, engineers default to peak provisioning. They drastically over-allocate hardware assets to ensure the system doesn't crash during execution. The result is heavily fragmented infrastructure, where millions of dollars are burned on idle cloud compute. Brute force monolithic AI development is financially and physically bankrupting production systems. The architectural antidote to this massive overallocation is intent-based compilation. Murakkab achieves this by entirely decoupling the high-level goal of your application from the physical hardware execution path. Instead of scripting rigid, sequential model steps, you provide a plain language description of your intent. The compilation engine actively analyzes that target goal and automatically maps out which specific tasks can execute simultaneously. It routes these tasks using a live constraint matrix, selecting the most efficient open-source models and tools from an available pool. This matrix evaluates priorities in real time, deciding if a specific task requires ultra-low latency or if the priority is achieving the absolute lowest cost. By translating your intent directly into dynamic routing, Murakkab removes human guesswork from hardware allocation. Once the intent is compiled, the system moves to physical execution through resource-aware compute sharding. To understand sharding, you must recognize the massive architectural difference between heavy, cloud-hosted deep learning transformers and lightweight, local neural networks. Invoking a massive cloud model to process a simple step that a local network could handle incurs an enormous energy penalty. Murakkab physically fragments a complex workflow, routing these subcomponents to their optimal hardware scale based on the constraint matrix. MIT and Microsoft tested this sharding architecture using intensive video QA and code generation trials. As this dual bar chart shows, Murakkab handled these complex workloads while consuming only 35% of the computational resources required by a traditional deployment. This efficiency translated to a massive 10x reduction in energy usage, slashing total consumption by 73%. Crucially, this 10x reduction in energy was achieved with a statistically negligible 2% drop in accuracy. Computational intelligence is the mathematical precision of matching the tool exactly to the scale of the task. In live production environments, data is volatile and task complexity fluctuates unpredictably. If you rely on a rigid, static pipeline, it will inevitably crash or overconsume when faced with sudden parameter changes mid-task. Murakkab prevents this through runtime adaptation, dynamically throttling the system architecture on the fly. This brings us to a strict reality check for your upcoming technical interviews. Recruiters are actively testing your understanding of operational scales. If you fake your foundational computer science knowledge here, you will be rejected. The ultimate indicator of an inefficient builder is defaulting to a deep learning model with a 100x energy cost when a local neural network could accomplish the step perfectly. The Murakkab architecture proves that the tech industry now prioritizes infrastructure optimization over raw generative output. Career longevity in the 2026 market depends on the ability to engineer real-time structural adjustments into the pipeline. To adapt your project-based learning for this semester, you must change how you engineer your backends. Stop designing pipelines that assume infinite server resources. Instead, you must master the logic behind dynamic graph orchestration. This involves designing multi-agent execution paths that expand, contract, and adapt dynamically to the workload. These adaptive graphs must autonomously reroute themselves based on live fluctuations in task complexity and physical resource cost. The era of lazy prompting is officially dead. With the physical limits of compute now clear, recruiters are prioritizing infrastructure architects who know how to govern token efficiency and minimize system overhead. Focus your time on building lean, secure, and physically efficient system architectures. If you want a full coding tutorial on how to implement intent-driven resource scheduling in your next Python multi-agent system, let me know in the comments. MIT and Microsoft have proved that brute force AI development is over. The future is owned by those who can engineer resource-optimal logic. Class dismissed.